Good afternoon, everybody. My name is Janelle Bailey. I'm the president-elect of the organization, so I'm glad to see you here. It is a delight to introduce you to Dr. Kimberly Ennico Smith. As George mentioned, Kim and I first met, I won't say the year, many years ago, when we were both undergraduate students doing an REU summer program at the University of Wyoming. And Kim and I were roommates, and I was in awe of her from the very beginning, because she is just amazingly brilliant and talented, not only in her science, but in her life. And when you follow her on Twitter and Facebook, you get insights into things that are not necessarily scientific. Her wonderful love of tea and all things belonging in the UK, and foreign and ancient languages, and wonderful, wonderful, delightful things. So really, really excited to see the path that she has taken to get to where she is, and to have her here today. So as I mentioned, we met as undergrads. Kim did her undergraduate work at Johns Hopkins Physics Department, where she was the president of her SPS chapter. So her connections with related organizations go back quite a bit. She did a PhD at Cambridge at the Institute for Astronomy, and then went to Steward Observatory to do a postdoc. And we did not overlap at our time at Arizona, but it was nice to know that we had similar places. Currently, she is at NASA Ames, except working out of Boulder, right, temporarily, and is the deputy co-investigator, deputy principal investigator for the New Horizons mission. So all these wonderful things that you've been seeing over the last 6 months about Pluto are just really exciting. And I'll tell you, I asked Kim to come and talk at last winter's meeting, and we couldn't make the schedule work out because of some previous commitments she had. And so then we talked about summer, and we're like, New Horizons arrives at Pluto about 10 days after our meeting. She's probably going to be a little busy. And so we're really glad to have her here, and the beauty of the delay means that she gets to tell us all some of the wonderful findings. So without any further ado, Kim Ennico Smith.
Oh, okay, sweet. Hope you can hear me. Wow, that's awesome. Well, thank you, AAPT, for inviting me. This is a wonderful opportunity to share with you things that I've been learning and hear things that you've been learning as well. This was at the Applied Physics Lab in Laurel, Maryland, which was where we operate the spacecraft, New Horizons. And I've been working on New Horizons just for the last 4 years. So it's a relatively new adventure for me. And then if you want to follow me on Twitter, I'm Ennico Smith, and I'm always talking about tea, but I'm also talking about other things I find interesting, because I love sharing what I learn. And I love engaging with people and having questions and answers back. But you can only do so much in 140 characters. As I said, I've been working on New Horizons just for the last 4 years, but I do a lot of other things as well. I'm very grateful for my physics education. This is me playing with my toys, because girls have toys too. I have built instruments that have crashed into the moon. I have built instruments that have flown on aircraft. I've built instruments that have flown in space, and instruments on ground-based telescopes. I've taken detectors to particle accelerators, and we're told to kill the detectors. I do a lot of fun things. But here I'm going to tell you about Pluto. I'm just going to say that I'm very grateful for my physics teachers in high school and college, and the encouragement that I received. Another neat thing, this is the New Horizons, this is a quarter of the New Horizons staff. This is a mission it's unusual for me, because 1/4 of the people working on New Horizons today are women. This is very different from the 3 other space missions I've been working on, where I would be the only woman or one of 2 women in a room as big as this. So I'm hoping the landscape is changing. It's a data point of 1, make what you will with it, but it's just been really fascinating. And experiencing the flyby, which is a historic moment, sending a spacecraft to a new world for the first time. It had been a very long time since the Voyager program. I mean, I was a junior in high school when Voyager 2 flew by Neptune. And so it was kind of neat to be part of it. But another highlight of the summer was I was made into a Lego figure, which was kind of amusing. There's this woman up at MIT. Who's shown here is Maya Weinstock, who's a STEM educator outreach, does a lot of work she's based in Boston. Alice Bowman, who's our mission ops manager, and then Kathy Olkin, Leslie Young, and myself were the deputy project scientists, so it was kind of neat. Okay. So I was going to have a preamble saying, in a part of the solar system far, far away, Pluto. This is what we knew of Pluto. So I go through the story about New Horizons flying past Pluto and the wonderful science and the physics. In fact, there is yet to be written the book of physics on Pluto, or a course on the physics of Pluto, because we are touching on some very interesting territories. It's an image from the Hubble Space Telescope. Is our best image of Pluto until this summer. 200 meters per pixel. Now, when you can get over 2 orders of magnitude and better spatial resolution, you get that. Now, this is what you get for flying a spacecraft near an object. So we are living in an era where our views of our solar system are being challenged. I mention that because this is a new view of the solar system. What's shown here, those circles, are the orbits of Saturn, Jupiter, Saturn, Uranus, and Neptune. And what's shown here are the discoveries of bodies in the outer solar system, the third zone. In the lower right is the year of the discovery. The diameter represents the size of the object artistically. Pluto was discovered in 1930. It was an oddball. It is now joined by lots of friends. This is the Edgeworth-Kuiper belt. It was hypothesized in the 1950s and 60s and has been discovered in the 1990s and in the 2000s. And it's the discovery of these other trans-Neptunian objects, Makemake, Haumea, Eris, that opened up the discussion about the status of planethood and also what our solar system is the structure of our solar system today. And as you got a sense, this outer solar system is quite numerous. And it's also not quite all in the plane. It's more of a torus. This is just basically because we're starting to discover with bigger and bigger telescopes, because these objects are small and far away. You can go to the Harvard-Smithsonian Minor Body Center and download a picture of our solar system. This is a solar system from yesterday. I was going to about download today. As you can see, the most numerous objects are beyond the orbit of Neptune, and Pluto is amongst its friends. This is our new views of the solar system. The mission to Pluto, New Horizons. When you design a mission, you want to have mission objectives, so therefore you can design the right payload to take the pictures. And so New Horizons is designed to characterize the global geology and morphology of Pluto and Charon. Charon is Pluto's largest moon. Map its surface compositions and characterize the atmosphere. We knew a lot about Pluto and a little bit of Charon from ground-based work, but Pluto and Charon are points of light. It's only with the Hubble Space Telescope that Pluto is 10 pixels across, and now with the Keck telescope and the larger 8 and 10 meter telescopes with speckle imaging and adaptive optics, you can get a few pixels across Pluto and Charon, but they are always just distant points of light. So putting together a spacecraft to go to Pluto, to meet those objectives, there are cameras, there are spectrometers, and there are particle detectors, so you can look for the interaction of the solar wind with Pluto and Pluto's escaping atmosphere. I also wanted to mention there's an instrument called the SDC, a student dust counter. It's actually built by students at the University of Colorado in Boulder. It was designed, built, and managed. They even had project managers as part of the team. Did all the integration tests, did all the necessary qualification tests, and now are operating the student dust counter. To get to Pluto, it's just far, far away. It was launched about 10 years ago from Cape Canaveral, and it's traveling on the order of about 36,000 miles per hour. That's about 1.2 million kilometers a day, or about 3 astronomical units a year, an astronomical unit being the distance between the Earth and the Sun. So to go to an object that is several tens of AUs away, you need to travel very fast but very long period of time. And so this is a picture of the direct transit across the solar system They had a gravity boost from Jupiter about 18 months after launch. It saved 3 years on the mission across the deep and encountered Pluto. Pluto and its moons are on its side, and I'll show you some more information about that. And this led to a very interesting trajectory design. The red line is the spacecraft trajectory. We went through the Pluto system, tilted on its side like a bullseye. This unique geometry allowed for the spacecraft to actually travel in the shadow of both Pluto and Charon and look back. And these are called occultation measurements. The sun is off to the right. It became a unique moment to actually measure the atmospheres and search for an atmosphere around Charon, where you just crossed the system in a matter of hours. So before getting to the science of Pluto, just some perspectives. Pluto is about 18% of the diameter of Pluto is about 18% of the diameter of the Earth, and about 66% of the Earth's moon. So Pluto is smaller than Earth's moon. Charon, Pluto's largest moon, is half the size of Pluto. So I'll give you some rough numbers there and superimpose it on the United States. So it's small. Pluto's orbit is highly inclined, and it's elliptical as well. So there are points in which it's closest to the sun, around 29 AU, and places where it's furthest from the sun at 49 AU. It's a big difference, and I'll get to that in a moment of the importance of that. When we flew by, Pluto was about 33 AU from the sun. Why do I mention that? If you apply the inverse square law, you can calculate how bright the sun would look if you were standing on the surface of Pluto. Pluto is so far away, and you would think that it would be pretty cold and dark there. It is definitely cold, but I wouldn't say it's dark. In fact, all the images you see of Pluto and Charon, the moons, are all reflected from our sunlight. Being about 33 AU away from the sun at the time of our flyby, and we also had to set the exposures of our cameras, 1 divided by that distance squared gives you a relative distance of how the brightness of the sun would look compared to the Earth, compared when you're on Pluto, compared to that of the Earth. And you could work the math and get a sense and realize that sunlight on the surface of Pluto is around 350, 370 times brighter than walking in full moonlight here at Earth. So you can see shadows, and so you can. If you Google Pluto time, it gives you an opportunity to know, when to take a picture where you are right now on the planet Earth, when it would be high noon on Pluto. And you'd find that high noon on Pluto, lighting conditions you could read by. So that was kind of neat to put that into perspective. The orbit is highly inclined. And another thing is Pluto is highly tilted on its axis. And this is interesting to help us understand what the data is showing us because of the interesting seasonal connections. Pluto is highly inclined at about 118 degrees, very different. It's very similar to Uranus. It's most likely just a result of how it was formed, but it's a very different geometry. So when we flew by Pluto was roughly this position on a schematic around the sun. Its orbit around the sun is 248 years. So 248 years ago was when the Mason-Dixon line was being mapped. Its north pole was pointing towards the sun at the end of the American Revolutionary War. As we go through Pluto's orbit, it gets discovered here. So all this time we don't even know about Pluto. Pluto was only discovered 85 years ago. So it hasn't made a complete orbit since its discovery. It was discovered in 1930. And around the time of its discovery, its south pole was facing the sun. And then we go through other landmarks. Its largest moon was discovered in 1978, and now we come to the flyby. It's spring in the north in Pluto, where the northern section of Pluto has been seeing sun for hundreds of years. It's a very different climate. Why do I bring this up? But you do a calculation on how much sunlight the different latitudes of Pluto get over its lifetime, or even over a year, or after millions of years after it's gone through this 248-year cycle, with the fact that it's tilted at 118 degrees, you will see that this is a plot of the amount of sunlight versus latitude where latitude 0 is the equator has the least amount of sun, and the poles have the largest amount of sun. This leads that the coldest bits of Pluto are at the equator, not at the poles. So this has implications for understanding and interpreting what's going on Pluto. So the discoveries, just some highlights. Pluto has mountains. This was one of the earliest images that were sent back. It was taken about 15 minutes prior to closest approach. In most of these images, I'll show a map of Pluto on the top right, and the orange dot represents the area that I'm looking. Pluto has a rotation of 6.4 Earth days. So when we flew by, we only got to see one hemisphere in great detail. The other hemisphere we observed 3 days out, but at much poorer resolution, very similar to the Hubble resolution. So we're piecing together the whole story of Pluto because its other hemisphere, which is also very intriguing. But these mountains on the southern part of Pluto, on this encounter hemisphere, which is also coincidentally the opposite hemisphere to what it's showing to Sharon, they are 3,000 meters in height, 12,000 feet. They're as tall as the Rocky Mountains. It was confirmed by another picture from a different instrument taken after closest approach, where we had a higher solar phase angle. This is very similar to a photography technique that you'd like to take your pictures at sunrise or sunset, because if you take your pictures at high noon, you don't get shadows. And here, we're able to actually confirm the heights of the mountains by looking at its shadows. And these mountains on the southern tip of the Sputnik Planum, which is a large glacier on Pluto, is very breathtaking. Triton, Neptune's moon, does not have these mountains. It's a big, big discovery. So to have a small planet that's big on fun, you can ski on Pluto, and this is certainly a fun topic. It's another lecture on working out the equations of physics for skiing on Pluto, because you're not skiing on water ice. You are skiing on exotic ices of nitrogen, methane, carbon monoxide, and then wonderful mixtures of the many combinations. Pluto has glacial flows. A stunning image. Glaciers are seen in the solar system. We have glaciers here on Earth. The Mars has the polar caps and evidence of old glaciers. But Pluto joins the planets that have glaciers. And you can see it by looking at the flow in and around obstacles, and even into the inlets. So even by looking at a picture like this, we're getting a sense that there is something dynamic going on in Pluto. The stunning imagery is every time we looked at an image coming down, we are just amazed by what we see, because each part of the terrain of Pluto is slightly different. So I'll move from the north down a little bit further south to a region that's known as chaos. Chaos just means it's just broken up. There are chaos regions on Europa and on Mars, but this is a different type of phenomenon. These are made out of ice and rigid blocks of ice floating on other blocks of ice. Because when you're at the low temperatures of Pluto, in the 30s, 40s, and 50s kelvins, at the low pressures of the 5s, 10s, 15, 20 microbars, you have some very interesting chemistry and physics going on with these exotic ices. So our hypothesis is these may be chunks of water ice, which at those temperatures and pressures are extremely brittle. They're hard like rock, floating on a denser nitrogen bay. Zooming in a little bit further, we see structures like this, these outcrops of material in the midst of a glacial field. This led to the inspiration of some art that was quite fun to see. See the nitrogen glaciers of Sputnik Planum that flow among mountains of pure water ice. Again, imagery of exotic places, but they are in our solar system. It's a one of a kind to have these things happening, and this is the beauty of space exploration. Visiting a place for the very first time, finding things exceeding your expectations, and lots of physics problems to solve. Pluto may have ice volcanoes. Again, the southern part, and I'm going to zoom in on an area that I've circled here, right Mons. which is elevated from its surface by about 4,000 meters. But in the midst of this high mound that's 100 kilometers across, 4 kilometers above the sea level, as you would call it, has a big hole in it. In addition, it's got what looks like effluvial flows. Okay, with a flyby, we're not in orbit. We only have these few pictures to take pictures, pictures to make sense of what we're seeing. So although the jury's still out on whether this is an ice volcano or not, it shows the geological signatures of being that. And when I say ice volcano, it's not powered by magma. It's actually powered by perhaps these are called clathrites, which are methane interspersed with these exotic ices that under different types of pressures could exude sludge-like activity and spew out. What the internal heating for that would be, unknown. The ice geysers on Triton are fueled by Neptune's influence. On Pluto, these seem to be dormant or old, but we're not really sure. But if they are confirmed, it is a new thing in the solar system. Pluto appears geologically active. The geologists like to categorize things as old, because everything is either giga-years old or hundreds of millions of years old. What's striking about the left side of the Tomball Regio, which is the heart of Pluto, is the fact that there are no craters. And this image is shown that you can't see any craters smaller than 400 meters, and we've got some snippets of data that are resolutions of 70 meters per pixel on Pluto and still can't see craters. Cratering, measuring the craters is a standard technique to date the age of a surface. You look up at the moon, it's full of craters. Areas that have had a lot more craters are older because they've seen a lot more impacts. But it is striking that the area of the left-hand side of the heart is absence of craters. And then there's a few craters here, indicating this is a very young surface, maybe about 10 million years. This might be slightly older at 100 million years. And then the rest of this is most likely at the formation of Pluto, which is around 4 giga-years. Complex terrains and compositions. This was quite surprising, this image that came down. And it's actually led to an interesting discussion about the physics of much of what's going on. Again, we're still focusing on the Tomball Regio, this glacial place on Pluto. What's striking is polygons, if you can make those out, 30 to 40 kilometers in size. Polygons have been seen on Mars, but the cause for polygons on Mars has been understood to be a freezing, thawing kind of motion. Polygons have been seen on the Earth with dry mud flats, where they leave when you have the evaporation, leaves behind these things. And a third theory that is being supported by other pictures that add to our combined knowledge of how we're interpreting these surface features is convection, some sort of internal heating that is leading to these warming from below, warming the nitrogen ice, making these convection cells. Then as cells become a little bit more buoyant, they're floating. As they cool down, they'll sink. And this sort of cycle of convection to heat from beneath and then cooling and sinking do lead to polygon structures that have the shapes observed on Pluto, more rounded edges. An indirect evidence is sort of seeing these dark bits, which are the models that the team's been working on. The floating dirty ice, dirty water ice that is rock-like, could be just lifted up by this convection going on. And in some cases, the convection fails to form a cell, and we see features like that. Evidence that we're seeing sublimation occurring on grand scales is the formation of these pits. These pits are 1 to 2 kilometers in size. What you see here. They're also surrounded by dark material, and they have an interesting arrangement that they're actually orientated on the north-south line. This is sort of giving an indication that there might be related to the amount of sunlight that the Pluto has seen. That's why I had mentioned it's important to remember that Pluto is highly tilted on size and has very interesting different seasonal structures. Again, everywhere we looked on Pluto, we kept on seeing more and different terrains, more of these pits. The closest that we are thinking of are sun cups, except the sun cups on Pluto are 1 to 2 kilometers in size. This is done by the sublimation of at high alpine valleys where the snow is evaporating and creating these crevices. So this is what we're currently thinking is leading to the fact that we're seeing a lot of active activity on Pluto that is related to its seasonal cycle. More and more of this bladed terrain. These are elongated, but they're also located north, so they run north-south as well. These are ridges that run for hundreds of meters. They're several meters, several kilometers in height with crevices, have distinctly colors, and we've never seen any sort of this terrain in the solar system. So that was a sort of a snapshot of some of the interesting terrains, and I'm going to segue more into the chemistry of Pluto because I find it just fascinating. And every discussion that I'm participating in, we're also kindly going back to our physics roots and trying to understand what might be seen. The colors of Pluto. What I'm showing here is a color composite. The instrument, the color camera board in New Horizons does not have a green filter, so we've made a couple of enhanced color products. The filters that we're using are near-infrared red and blue. We knew that Pluto had these ices who had the strongest signatures in the infrared. But when we put together a color composite image, we see some structures in the color. There's this equatorial band that's very dark and very red, and actually very near infrared. The heart is broken into 2 different colors. The left lobe is more orangey, and the right lobe is less orangey, more blue. The northern pole has a much more yellowish tinge to it. Now, you have to think about the context of where it is with relation to the pole from the equator. We have some distinctly latitudinal colorations on Pluto. This is giving us a clue, perhaps, to what's going on Pluto's surface and what has been placed on Pluto's surface or what's being removed or covered up. So Pluto is very colorful. It's actually quite red. And so essentially the second red planet, and the other red planet in our solar system. The Arctic Circle is drawn about there. And so the northern pole has been seeing constant sunlight for 100 years. Actually, it's starting its 100th year cycle about 20 years ago. So it's 20 years into a 100-year cycle. So we are seeing some interesting seasonal effects now. But this was the face of Pluto that we got to see. Looking at Pluto in more detail in color, we're noticing different things going on. The rims of the craters in this region are methane-rich, and I'll show you a map of methane-rich. In other cases, the basins of the craters are this dark color. Spectroscopically, they match a type of hydrocarbons called tholins. Tholins are soot-like particles that have been photolyzed or UV radiated and have these hues going from yellow to red to brown. And it's our hypothesis that the coloring agent on Pluto is due to these tholins. Going back to this chaos region, because now we can go to the Il-Ezagi Mountains, which are on the highest elevations. They're about 5,000 meters, so taller than the Rocky Mountains. Zooming in even further, because we have imagery down to about 70 meters per pixel, we have dramatic images of the mountainous terrain intersecting with these glacial sheets. And what's interesting, if we go back, that they're layered. There are Certain sides of the mountains show coloring, which is we're understanding to be tholins. But how can you have coloring on the same surface at different altitudes? One hypothesis is thinking about how you have coloring in the Painted Desert in Arizona, where you have seasonal deposits, the seasonal deposits being the snow. So if you were to look at this type of terrain at the right time, you will see two different colorizations. At a slightly different season, you'll see slightly something different. So you can imagine a lot of, over many years, that the terrain will change. And you're looking, could we use the coloring on, the layering coloring on Pluto to help us understand the dating of what's going on Pluto? And this is active work we're working on now. Pluto's spectrum. This is a spectrum of its reflective albedo versus wavelength from 0.85 to 2.45 microns, so it's the near infrared. And we knew a lot about Pluto. It's a distant point of light, but you can get a hemispheric average. Pluto is rich in methane. That's what those deep absorption bands are. So we knew Pluto's surface to be methane rich. We also knew it had carbon monoxide on its surface. And we knew it also had nitrogen. And nitrogen had been discovered in its atmosphere through occultation measurements. But the dominant ices, the exotic ices of Pluto, are methane, carbon monoxide, and nitrogen. With the infrared mapping spectrometer on New Horizons, we now have a spatial distribution of these ices, which we didn't have before. And they are sometimes correlated with the geology beneath it, and other places they're not. So it's an interesting puzzle to deconvolve, but it's a very powerful, now we have hundreds of pixels across Pluto with spectral information. What I'm showing here is on the top is the brightness represents the depth of the feature, so the more abundant of methane, nitrogen, and carbon monoxide. And below was superimposed on our panchromatic imager. A couple things to point out. The carbon monoxide is highly concentrated into the left side of this heart. We're trying to understand why that would be so. In more detail, with the methane maps, methane is everywhere. Well, for the most part. It is definitely seen at the North Pole, on those crater rims, in the heart, the Tomball Regio, and this Tartarus dorsa, the bladed terrain. Very strong methane signatures. It is surprisingly absent, or maybe just covered up, in the Cthulhu region, which is an older part of Pluto, has more craters, and is heavily colored with this tholins. Nitrogen is another mystery that we're trying to untangle. Concentrated in the left side of the heart, and is also seen in the basins of craters. So if methane's at the rims and nitrogen's in the basin, what's going on with these exotic ices with altitude? And it is surprisingly absent from the north and in the equator region. But again, could the nitrogen be masked by something else or covered up? This should be a familiar diagram. In fact, we're going back to basics on the states of matter. With our solid, liquid, and vapor, with temperature rising on the y-axis and pressure increasing on the x-axis. You have your freezing and your melting when you go from solid to liquid. You have your condensation and vaporization from liquid to gas, and then you have your deposition and sublimation from the solid to vapor state. On Pluto, we have looking at the methane and nitrogen phase curves, and the Pluto's temperatures are between 30 and 50 Kelvin, and pressures of 5 to 20 microbars. We've actually measured Pluto's pressure at 10 microbars over one particular place, but it could have a range over its history. To look at what's going on is a lot of sublimation and deposition of the methane and the nitrogen species. Water is just shown up here in comparison. Water behaves as just rock. So we just think of water as rock, because this was a big surprise. Oh, I'll get to that in a moment. This is the other thing to keep in mind. is we are now going back to tertiary phase diagrams where the actual percentage of methane and nitrogen is important. So it's not just this methane by itself. If methane is diluted in nitrogen, its wavelength shifts blueward. We can measure that with our spectrum. So we're fitting our spectra now and finding that we have different percentages of nitrogen hidden in the methane. And at the temperatures of Pluto, there are actually two different phases of nitrogen and methane that we're measuring. This is the importance of laboratory astrochemistry, where we can actually take known states of nitrogen and methane and percentages, put it to the right temperatures and the right pressures, and come up with laboratory databases that we can match our spectra. We are seeing enough changes in the lines of methane to help us understand how much nitrogen is really hidden in there. So we just started this work as the data is just very complex where you look on Pluto. Water. Water has been discovered on Pluto. Water had not been known from the ground-based measurements. And it's, interestingly enough, concentrated in the dark regions. And it also has some outcrops. Outcrops where these mountains are. The mountains are now kind of understood to be water-rich, rock-like floating icebergs on the seas of nitrogen ice. So that cartoon is turning out to be reality. He was very lucky in his guess. And water is missing at the pole, but again, could it just be covered up by something else? Pluto has blue skies. This stunning image was taken about 15 hours after closest approach, looking back at Pluto. And the atmosphere is lit up. We did not expect to see the atmosphere lit up. To see this in the visible camera is implying that the particles are large to see the scattering. These haze layers extend up to 200 kilometers in altitude above the surface. And they extend for thousands of kilometers and have layers. Just a stunning imagery. Makes you appreciate just the beauty of looking at just something for the first time and also trying to make sense of what you're seeing. The story gets more confusing. The skies on Pluto are blue. So this image is taken with a different camera that has color filters. And Pluto's atmosphere is blue. And surprisingly enough, Pluto's atmosphere gets bluer as you go higher. We understand the blue coloring is from scattering by small particles. How can you have haze big particles, have brighter images at the lower elevations because they are big particles, and yet have smaller particles higher up? So we're working computations to explain, are these a term called fractal aggregates? Or we start small and then we get big and we're raining down. Pluto's atmosphere is definitely there. It is definitely different than had been anticipated, and no one had thought it'd be dominated by very small particles high up and significantly larger particles lower down. In some of the images, we actually see fog in the basins of the craters. It's just a crazy place. And big other surprise is Pluto's atmosphere is not as extended. This is what the theorists had thought Pluto's atmosphere would look like based on, playing around with gravity, playing around with Jean's escapes, doing those equations, making assumptions of what Pluto's atmosphere was made out of, to be extremely extended, tenuously held on by Pluto's low gravity. The data indicates that the atmosphere is actually much more compact and colder in its upper atmosphere. Last night at the plenary, I was learning that our Earth's atmosphere has a colder upper atmosphere and our warming up lower atmosphere. Well, we've learned with the New Horizons data that Pluto's upper atmosphere is colder than they thought as well. Pretty interesting to think about. And putting it in perspective with Charon, which I'm just going to get to in a moment, Charon is in orbit around Pluto of about a distance about 20,000 kilometers. It had once thought that Pluto's atmosphere might have been interacting with Charon, but now that the atmosphere is quite compact, that idea is going away. Charon, I think, is a sleeper hit of the summer. Charon and Pluto have a very interesting relationship, very similar to Earth and Earth's moon. It's understood that Pluto and Charon may have been formed by this giant impact that spewed off the two bodies. Pluto and Charon are tidally locked. It means the same face of Pluto faces the same face of Charon. What's shown here is the orbit of Charon around Pluto, and the X marks the barycenter, the center of which the two objects orbit around from their relative gravities. And in the Earth-Moon system, that point is still within the Earth. Because Charon's about half the size of Pluto, has a slightly similar density, might be a little lighter, the barycenter is actually outside the planet Pluto, and that may lead clues to what we're seeing with the other moons. Charon is relatively gray in color compared to Pluto. What's shown here is an early picture of Charon where we discovered it has a red polar cap on its north pole. We can't see the South Pole because of our viewing geometry, and the calculations are suggesting that there should be red poles at both ends because this might be a cold trap. So in this case, the coldest bits of Charon are at its poles where tholins could migrate to. It's relatively gray with a red top, and that was a big discovery to see that Charon is not as just uniform in color as it had anticipated to be. It's got this chasm that runs through its almost equator. It's about twice as wide as the Grand Canyon, 4 times as long. It's this massive, big chasma, tectonic belt. Below the belt is more younger terrain, a lot of smooth plains with a few impact craters. So the team had predicted that Charon was just going to be old and battered and had lots of craters, which has relatively few craters. It's got these sunken terrains, these mountains in a moat. We don't understand how they could be formed that way. Were they formed in situ, or was it the fact that the terrain around it was modifying? It's got craters with bright rays. It's called lobate ejecta. It's when an impactor hits a surface that has been covered with some sort of ice material, creates these rays that have a higher reflectance than the surrounding material. And it's got this red spot, the pimento in the Charon. Charon's spectra is very different than Pluto. If they were formed by the same object, why do they look so different? Here again, well, on the same scale as the Pluto, 0.85 to 2.45 microns, its dominant spectral component is water with a little bit of ammonia. So to have two bodies so close to each other with a common origin, and the fact that their main surface components are totally different from each other, is a huge mystery. And we have mapped water all over the surface of Charon, and ammonia is in isolated impact sites. So it had been detected from the ground, but now we know where on Charon's surface this ammonia. This plays an important part, because if you have water and ammonia together, you get different types of physics in terms of energies stored up, densities, trying to understand what's going on. No more new moons. If you had followed the mission very closely, you would have noticed that Pluto has actually 5 moons. Charon had been discovered in 1978. Nix and Hydra had been discovered by Hubble Space Telescope in 2005. The mission launched in 2006. In 2011 and 12, 2 other moons were discovered. When they discovered these more moons, they're like, there must be more. So it became the highest tall pole of the mission. Can we get through the Pluto system alive? Because if you're traveling at 36,000 miles per hour, something the size of a small grape can knock out a vital system. And we didn't have Kevlar, we didn't have any of this special, we were trying to be the lightest spacecraft to get the highest escape velocity off the Earth. They weren't even thinking about putting shields up. So all the months leading up to the encounter was actually staring at the Pluto system, and we were basically monitoring the moons that we knew about and then searching for the moons, for new moons. There were no new moons. It was just amazing how, with Hubble, yes, it's a wonderful telescope, that we certainly were trying, we couldn't detect things down to the hundreds of meter size. So here are the moons of Pluto. Family portrait. We've got Charon, and then Styx, Nix, Kerberos, and Hydra. So Nix and Hydra are around the 35 to 60 kilometer size, and Styx and Kerberos much smaller, on the tens of kilometer size. Two of them, Kerberos and Hydra, tend to be bilobal. It's very similar to the ESA Rosetta mission comet, which also looks like the rubber ducky. It's got two lobes to it. Whether or not this is common, statistics of 4. But we can also have fun, because when you look at these objects and you see them at different angles, you start coming up with, I thought that looked like a recliner chair before. This is what we do, we scientists do. And these small moons are chaotic. Putting together those light curves, this is a movie that a colleague of Mark Schoelker made based on the rotations. This is a huge mystery. The outermost moon, Hydra, has a rotational period of 10 hours. They were formed 4 gigayears ago. Why haven't they slowed down? Why haven't they gone into some tidal thing? The fact that there's that Charon there, and there's the barycenter, is the activity of having these two bodies, a binary planet influencing. So the chaotic moons is a big, big mystery. And also, even in the last 2 years of Hubble data monitoring the light curves of Nix and Hydra, Styx and Kerberos, Nix itself has actually changed its rotation speed in the last 2 years. So it's nothing stable. Spinning tops. So, some conclusions. Discoveries by New Horizons of Pluto and its moons, mountains. We haven't found mountains. This is the mountains of farthest out in the solar system discovery of mountains. There are glaciers and what looks to be lots of glacial flow-like activity. There may be these ice volcanoes. And if that's that's a discovery, it's the first of its kind in the outer solar system. We have this juxtaposition of the young surface and the old surface. Clearly something happened to Pluto's past. What is that glacier? It's made out of nitrogen and methane ice and carbon monoxide. It's coming from underneath, but how did it form? Why is it stable? That's the source. Is that the source of Pluto's atmosphere? Is it moving to other parts of the planet? It's very colorful. The colors of Pluto will be the key to unlocking what might be going on this intriguing world. And scientists, we like to play with the different, just like with photographers, you like to play with your hue and your saturation because it draws your eye to certain features. Then you can go back and look at the Borg graying visuals and go, aha, I now see layering that I didn't see layering before. It's because we do play with the color scales a lot. It's got blue skies and a very compact atmosphere. So a world with an atmosphere and not as escaping as they'd like. In fact, there is still a lot of physics to be done on the atmosphere of Pluto, mainly from the escape rate. It's a perfect laboratory for just testing basic physics of the escape rate of nitrogen and acetylene and ethane, because we found all these molecules in Pluto's atmosphere as well, and trying to understand. So we have unique measurements to help constrain these models. And it has a diverse family of moons. So what's next for New Horizons? We made a burn to go to another object, and the object has 2014 MU69. It was discovered by the Hubble Space Telescope during a search for hazards and then looking for other objects that are in our trajectory path, because the limiting resource, one of the limiting resources of New Horizons is its fuel budget, which denotes how much thrusters it can puff to change its trajectory. Flyby will be January 1st, 2019. So 3 years from now. And the object that New Horizons will visit will be on the order of the size of Nix and Hydra, this 30 to 40 kilometers, a very different target. Perhaps truly a primordial remnant of our early solar system. As you can see that Pluto and Charon have had a history. Maybe this new object will actually give us some clues as to what's going on in our early solar system. So thank you for your attention. And follow the mission by just Googling New Horizons, Pluto. We have a Pluto picture of the day, the P-pod, that you can sign up and get pictures to it. And I'd love to see a course on the physics of Pluto, because the chemistry that's going on with exotic ices, the interesting seasonal effects, to actually have this rich data set to even probe some interesting questions is, starting new chapters on these icy bodies. And it would be awesome to send more spacecraft to visit Makemake, Vulcan, Orcan, Eris, all these wonderful other trans-Newtonian objects that look as chemically complex as Pluto. So, thank you.
Data download be completed from New Horizon?
It's a good question, data download. So our flyby, we filled up our solid state recorders. We took over 60 gigabits of data. We transmit at about a kilobit per second. If you do the back of the envelope math, it will take about 6 to 9 months to get all that data down. We can only transmit on the data we collected on the 70 meters. There's 3 of them. So we share time with other missions. So it take about 16 months from July of last year. We were about a third of the way through. And so yeah, 16 months to get the data down. So we're anticipating end of October, middle of November of this year to get all the data down. It all comes down to whether the 70-meter assets stay up. They're going through a lot of maintenance now, and so we've been down to 70-meter.
Other questions?
Yeah. Curious about 2 things that you said. One is Kuiper Belt is a very crowded place. There's a lot of stuff out there, and that the moons seem to be very chaotic for having been a part of Pluto's system for billions of years. Do we know that they have been a part of Pluto's system for all those billions of years, or is it possible there's still changes going on?
There's a lot of mysteries about the system. What we do know is the albedos, the reflectances of these objects, are much brighter than we are measuring the reflectances of the other Kuiper belts. So it was ruling out one of the hypotheses that the smaller moons were captured Kuiper belts from a time after the Pluto-Charon formation. So it's leading towards the hypothesis that the smaller moons were formed at the time of the Pluto-Charon formation, which adds to the confusion of why they are still tumbling and being very chaotic today if they were formed 6 giga-years ago. And so we're looking closely at the presence of Charon and that barycenter and the perturbances that having 2 bodies do on a system. But still, it's a system of one. We've never seen anything like it. All the other moons around Saturn and Neptune are well behaved. But so we're eagerly waiting the infrared spectra of these objects. We know its brightness is very bright. If the infrared spectra indicates that they're water ice, that will lead to some clues as well. But yeah, we don't have all the answers. But it's leading like they were formed back then, but why should they be chaotic now?
So the blue sky backlit picture that you show is really magnificent. And I wondered, it appears that there's an asymmetry that's probably due to the sun being off center a little bit, but it could also be because the atmosphere itself is not symmetric because the Charon, the moon, pulling a tidal bulge. Is there any evidence of a tidal bulge in the atmosphere of Pluto from Charon? That's
a very good question. In fact, you're right, there is an asymmetry, and I didn't go into great detail. One is there is an effect of where the sun is, But there is also a hemispherical where how much sunlight has been. And it is not necessarily the Sharon side of it. So there is a seasonal effect going on whether it's not due to a tidal bulge created by Sharon pulling on the atmosphere. The atmosphere is quite compact. And when we learned it was compact, we kind of ruled out is Sharon interacting with Pluto's atmosphere, because that had been one of the going-in hypotheses. But there is an asymmetry that we do need to understand a bit more. And you can see it in the data. Yeah.
You showed a tectonic bulge or a tectonic scar on Charon. Was there any evidence of tectonics on Pluto?
Some of the features that I was highlighting were primarily more of the glacial features. There are huge chasms northward of the equator that we need to look at whether there's tectonic activity. So it does look like, at first glance, when we made a first geological map of Pluto, we identified, okay, those look like tectonic features. But it's hard to say. So I'm sure it's on the table. It hasn't got much attention yet.
Thank you for the wonderful presentation. Are there any plans, even informally, to rename 2014 MU69 prior to New Horizons' arrival?
There will be, yes. I'm understanding that they'll be done through the appropriate channels with the IAU to appropriately come up with a formal name for it. Yeah, so the 2014 MU69 was discovered in 2014, and I forget what MU, there's a naming convention. But yes, we do want to have it named, have its own name.
I'm wondering how we define a North Pole. If it's tilted 119 degrees, how come the South Pole isn't the North Pole?
That is a very good question, and it's also apparently caused a lot of, when you have lots of other bodies in the asteroid belt that also don't have North Poles in the right place. This is a convention that was adopted to follow the right-hand rule, such that the rotation of Pluto is 6.4 days, the thumb is pointing in the north direction. So that's how it got decided.
Okay, we have time for one more.
Long live the right-hand rule. No, everyone could agree to that.
Thanks again for the talk. You mentioned 60 gigabytes of storage, is that what you said?
Yeah.
That seems a very small amount of space to send all the way out there. Does that have to do with the transmission rates, or?
That's actually the size of the recorders that we had. My iPhone has more storage in it than the solid-state recorders on New Horizons. Why we have a low transmission rate was actually a choice in the spacecraft design to get it to be, to decide on power. To have lower, if we had lower power transmitter, we could actually have another instrument on board. The total instrument suite runs at 29 watts. 7 instruments that run at 29 watts. And to do that, we also just had a lower transmitter power. Because it was basically a mission for the patient. If you're going to wait 10 years for the mission to get to Pluto, you could wait, a year and a half for the data to come down rather than having everything come down right away. But data storage was a limited resource, but it was sized appropriately because there's only so many pictures you can take when you're doing a fashion shoot flyby. You're taking pictures as fast as you can, as fast as the recorders can fill up. You have to trade between the 7 instruments. 2 of the instruments are scanning instruments that required the thrusters to actually scan the spacecraft while taking pictures at the same rate without being smeared. These beautiful pictures of Pluto is scanning a very tiny array across the whole planet. Pretty complicated. But yeah, it was designed, worked out, and optimized the space for what we had.
I'm sure many of you have more questions, and Kimberly will be here afterwards to answer any of those. Of those of you who didn't get a chance to ask a question now, I'd like to thank our speaker one more time for a great presentation. And this session is officially closed.